Hello everyone, welcome to Nevin's Data Lab. In this video, we'll learn about decision trees. Decision trees is basically a machine learning model which uses a tree data structure. It is a bunch of yes/no questions which is used to like classify or for even for regression. So let's look at this example. In this example, we can see that we have a root node. This is like our whole data set. And in the end, we are classifying them into either red or green. So while creating a decision tree, we have to keep these three things in mind. First is the split feature, second is the split point, and third is the stopping criteria. By split feature, I mean that at which feature should we split? Like we have to, and there might be a bunch of columns. So which column should we select to split the decision tree on? So for example, in this example, we have split it on the neighborhood column. Next is the split point. In the specific column that we selected, what criteria should we use to split it? Like there might be like east, west, north, south, etc. But we have only split it into like east and west. So even in the neighborhood, there's like a criteria in which specific criteria should we split. And next is the stopping criteria. Basically, when should we stop creating new nodes? Like why didn't we create another node in which we had all these three again? So we need to consider all these three factors. So first steps for doing that would be first to calculate information gain with each possible split. Divide the set with the feature that gives the most information gain, and then divide the tree, and we have to repeat this same process until we reach a stopping criteria. So what do I mean by information gain? Basically, the specific split should give the maximum amount of information possible. Like in this split, we can see that we already have to like, we don't have to consider this branch because we already reached the leaf node. Basically, this would give a good information gain. So for calculating information gain, this is the formula that we have. It's basically entropy of the parent minus the weighted average of the entropy of the children. And what is entropy? Entropy is basically the randomness of the data. So basically, if we look at this specific root node, for example, we don't have any green points. So the entropy would be 0 because there is no randomness. We already know what is in it. Let's say if there was like a green point in over here, then the entropy would not be 0. It would be like close to, I mean, it would be between 0 and 1. Let's say if there are 2 green points and 2 red points. So basically, it could be either of these two. So in that case, entropy would be the maximum, which is 1. So to calculate entropy, this is the formula, that is the minus of summation of probability of x log of the same thing. So in this case, p of x is nothing but the number of one sample. Like let's say this is 2. So number of 2 divided by 4 because there are 4 total data points. Next, we can talk about the stopping criteria. Stopping criteria could be basically the maximum depth. Like in this case, the maximum depth would be like 3. We can decide like how much should be the depth. That could be one of our stopping criteria. Next would be the minimum number of samples, that is in each root node, how much should be the minimum number of samples possible. And the next would be the minimum impurity decrease, that is uh, the change in entropy. If it's not significant even in the next split, then we can just stop building our decision tree. Okay, so now that we know the basics of decision tree, let's start building the code. Just like in the previous videos, I've created a class decision tree with init, fit function and predict function. We'll also like create a separate class for node in which obviously there would be an init function, and also there would be another function which is leaf node. In this init function, I would need the feature that it was divided into, the threshold it was divided into, the left subtree, the right subtree, the value. We can put it all in here. And his leaf node can be if return self dot value is not none. So if it is none, then it is a leaf node, and if it's not none, then it's not a leaf node basically. And this would also take in the self parameter. So yeah, now that we are done with the node, let's start with the decision tree class itself. We need the min sample split. We also need the maximum depth. We can initialize them both over here. What else do we need? We also need the root, which can be none in the beginning. Now we can move on to the fit function. So for fit function, what we have to do is like self dot root is equal to, okay, for this like I will create a helper function which would be like grow tree for example, and this will take in x and y values. Def grow. Okay, so this would be self dot. A good practice is that for using while creating helper functions, write in an underscore between, I mean before the name. We can start the grow tree function, so we will have to basically check for the stopping criteria. We'll also have to check for the best split, and then create the child nodes. So creating child nodes would be like calling this function again, so this would be like a recursive function. We can like initialize and samples comma and features below x dot shape, like in the previous videos itself. We are assuming x to be a numpy array. Next we can take in labels is equal to length of y, actually unique values of y, so we can just write it as that. So let's start with the stopping criteria first. As we saw here, the stopping criteria is basically max depth, minimum number of samples, or minimum impurity. So if the current depth, okay, let's take in depth also here. If depth is greater than max depth, then we stop, or if n samples is less than minimum samples, this is like min sample split self dot, and this would also be self dot max depth. So if this, or if the length of the labels is equal to 1, that is there's only one type of label, so we don't have to split it further, then we match the stopping criteria. Actually, sorry, not length of n labels, n labels is the length itself. So if we reach the stopping criteria, what do we have to do? We have to basically return the value, and for calculating this value, we'll also create another helper function. Value is equal to self dot, let's say, majority voting. So why are we taking the majority? Like I explained in this video, if this had like 2 reds and 1 green, then we would take red as the output because we are taking the majority basically. So that's why the value would be the value of the majority label. This would take in y, and this would actually be node of value is equal to value. Next we can actually define this majority, so this would take in self comma y. I'll actually write this down. So we had done this in the previous one in one of the previous videos. I'll just paste the code from over there. So this will basically return our most common value, I mean, which is basically the majority. Next, if the stopping criteria is not met, then we'll have to do best split. So for best split, before best split, we'll also have to create feature indexes, feature this would be like np dot random dot choice, and we'll take this and we'll set the replace is equal to false. Next we can go into the best split. So best split should basically give us a best threshold comma best feature, and let's create another helper function for this, self dot best split, let's say. This will take an x, y, and the feature indexes that we just created. So let's create the best split function as well. Self x comma y comma feature id x's. Since we are returning best threshold and best feature, I'll just create split threshold comma split feature, and I'll set them as none. And we'll also need best gain. I'll set it to -1 in the beginning. So let's iterate through all the feature indexes, and we can set x is equal to feature index. Let's change the name to x column. So the thresholds would be np dot inc of x column. Then for thresholds, we'll have to calculate the gain over here, and after calculating the gain, if gain is greater than best gain, best gain is equal to gain split feature would be the feature index, and the split threshold would be the threshold. So for calculating the gain, let's create another helper function. So this would be self dot calculate gain. We'll pass in the x column, the y, and the threshold that we are working with. Before writing that, I'll just return these two, threshold comma feature, yes. And let's start working on the calculate gain function. So like I said, this will take self comma x column comma y comma threshold. So how do we calculate the gain? Calculating the gain was with this formula, that is entropy of the parent minus weighted average into the entropy of the children. So calculating the entropy, let's again create a helper function. So entropy is equal to, let's say, calculate entropy of y, and I'll just define this as well. And how do we calculate this? We calculate this with this formula. So for doing that, we can like get np.bin count of y, and then divide this thing with the length of y. So this is basically getting the number of one class and dividing it with the total. So let's just set this to like probs, and basically we have to return the minus of np.sum of this would be p into np.log p for p in probs if p greater than 0. So that should be accurate according to the formula, p into log p, and then summing it up and then adding a minus sign. So now that we have calculated the entropy, let's go back to calculating the gain. This would be the parent entropy. Next, you can create the children. Creating the children basically means getting the left indexes and the right indexes. So for this, what we can do is like we can use argware in NumPy, and we can just do x colon less than or equal to the split threshold. Okay, it's just threshold. And we'll also have to flatten this because argware like gives in a column format, and we can do the same for the right indexes as well, but instead of less than or equal to, it would be greater. Now that we have created the children, we can calculate the weighted entropy of the children. Okay, now that we have the children, if left index is equal to 0, or actually the length of the, if there are no children, then just return the gain as 0. Next we can calculate, we want to calculate the weighted average of the children entropies, so we can just start by defining n, which would be length of y. Next we need the length of the left nodes, I mean all the left tree, and the length of the right tree. This would be basically the length of left indexes and the length of right indexes. Next we need the entropy of the left and the entropy of the right. We already have written a function to calculate the entropy. This would be basically self dot this thing, and this would be y of left indexes comma the same thing but with y of right indexes. Now we have the entropy of the left tree, entropy of the right subtree. We also have the lengths. So the weighted average would be n of L by n times E of L plus the same thing but with right. Next, the main thing, information gain. This would be the parent entropy minus this weighted average, which is of the children, and we can return information gain. Now that we have calculated the information gain, we can go back to the best split that we were finishing up. I mean, we have finished this best split, so we can go to creating the child nodes. So for creating the child nodes, what we need the left indexes and right indexes, and this can be calculated again in the same way that we did before. So that is over here, and instead of x column, this would be the x of the best threshold and the best feature, sorry, and this would be the best threshold. In the same way we can do it for this thing, greater than the best threshold. Now basically we can create we can call the grow tree function again. Left tree is equal to self dot grow tree, and grow tree takes in x, y, and the depth. In this case, x would be left indexes and y of the left indexes as well. The right tree would be more or less the same thing. Okay. Right indexes. Oops. Right indexes. Also, we'll have to give in depth, which was over here. Depth would be basically depth is equal to depth plus 1. Just copy this, and then we can finally return the node. Node needed all these things. So feature is basically our best feature. This would be best threshold. This would be left tree. and this would be right tree, and we'll just do this for now. So we have created the node as well. So I think we have finished creating the fit function. Now let's move on to the predict function, which is the last one. So for predicting, we would have to traverse the tree. So we'll create another helper function for that. Let's just say traverse tree. This will take in x, comma self dot root for x in x. This would take in x as well, and we can return the numpy array version of this. So let's start with the traverse tree function. This is taking in x and a node. So before traversing, we can check if the node that we have is the leaf node or not. So if node dot is leaf node, then we can return node dot value. If it is not the leaf node, then we'll have to check if the feature, I mean the feature is less than the threshold. And if it is, we can again traverse the tree towards the left side. So this would return basically self dot traverse tree left, else basically return self dot traverse tree right. This would be x of node dot feature, my bad. This would be node dot threshold, and traverse tree takes in x as well. So x comma node dot left comma node dot right, and this will take in self as well. Yep. So that's it for the decision tree function. Now we can test this code. Since this video has already been so long, I'll just try and directly copy paste the testing code. This is similar to what we have done in the previous models as well. You can just cross check. So I've called the decision tree model, and I am fitting it with the x train and y train, and then I'm predicting on the x test function. So let's run this code. Okay, so init function has two missing parameters. Okay. Okay, I'll just put in sample split as like 2, for example. Max step is equal to 100, and then just run this again. Depth group tree. This would have depth is equal to 1 for feature index. Okay, so while debugging, I found that we have to use like n features comma n features for feature indexes, and the other thing is that I can just initialize everything to none in for wherever cases in which I haven't already initialized. So let's try to run this again, and yes, as you can see, we are getting a 92% accuracy, which is pretty good. So yeah, that's it for this code. If you like this video, please do share, like, share and subscribe.